floor. Felix is working on the CarboSeq project at the Tunin Institute, and he's a member of EJP SOIL. And I suppose your area of expert Felix, is increasing carbon, soil organic carbon in agricultural soils at EU scales. And I suppose that the presentation that you're going to give this morning, the title is The Capacity of Soils to Store Carbon. So it's a nice starting point. It sets the scene, I suppose, so to speak. And over to you, Felix.
Yes, hello, thank you. Exactly. So here you see my screen, and today I will talk with you about the capacity of soils to store carbon. Exactly. So just a little reminder, we've all seen a form of this carbon cycle in one way or another. The key message here really is that soil stores about 1,500 petagram carbon up to 1 meter depth, while the atmosphere stores only half of it. So it is a very important storage of carbon. And in the carbon that we are interested in today specifically is the soil organic carbon, or SOC. And changes in the SOC are the result of an imbalance between the C fluxes. So basically the difference between the input and the output. And this SOC is controlled by soil type and climate. Those are two things that we can't affect very much, but there are two other things that we can affect, which is the land use and the soil management. The land use, also how much we can affect it or not, we can discuss this at another point. But really the soil management is something in our running agricultural systems where we can make change. Historically, the cultivation of soils resulted in carbon losses of about 78 petagram of carbon, and parts of this can be recovered with proper soil management. So what opportunities do we have to actually store carbon or to increase carbon? So what can we do for that? So as I said, we can improve the soil management towards an increased C input. One example you can see on the right, the cover crops. We can introduce those. They increase the time where the soil is not bare but covered. They bring more plant residues and also increase the root, which is all carbon that is additionally put into the soil if there were no cover crops before. However, these management options, they must be regionally specific. For example, in regions where there's no water, irrigation is hardly a choice. So we have to adjust our agricultural practices to different pedoclimatic regions. So the real question, I mean, we know all the theory for these things, but the real question that we need to answer is how much carbon can we actually sequester in Europe? And this is the question that CarboSeq tries to answer. So we want to estimate the soil carbon sequestration potential of European agricultural soils. It should be economically practicable and feasible. It should be based on tested and validated measures for carbon sequestration in agriculture, take into account economic costs, also account for the non-CO2 greenhouse gases, and also consider the subsoils. This project consists of 23 countries and 27 partners, as you can see at the bottom right. And this is how CarboSeq is built up. I will keep this part very brief. We are organized in work packages like any project, and we have made three main components. At the bottom, you can see the component A, what we call the management options. This is really the foundation of the project. There we create large databases organized in three work packages on cropland management, grassland management, and biochar and other amendments. Here we want to find out how does different management options affect the SOC content of the soil. But there are, of course, certain things that are a bit uncertain. And this is where component B at the top right comes into play. We called it uncertainties. So there we have three work packages that take care of non-CO2 greenhouse gases of the subsoil and the water logging. And these two components feed into the last component, the component C called modeling. In the modeling, we have two work packages, one that is doing the actual modeling based on the results of component A and B, and one where we need to find the real area of implementation. This is what I want to talk about a bit more today. So far, what we already know from many papers is this, what you can see here in gray, the theoretical C-sequestration potential, where you basically say, if we introduce cover crops all over Europe on every agricultural land, this is the amount of carbon we can store. But this is, of course, not very realistic because there are certain limitations, constraints. And these we try to get together and really implement these. So the first constraints that we've identified that we want to take care of are the, of course, biophysical or environmental constraints. So they limit our sequestration potential. For example, where you don't have enough sunshine or not enough water, you can't grow cover crops. So this is what we call the biophysical environmental carbon sequestration potential here in green. However, if there is somewhere water available, you could introduce a technical solution to enlarge the biophysical constraints or the potential. In this case, we could irrigate the fields and then we would have enough water for cover crops. But this cannot be still, this is not close to reality. Just imagine if we ask every farmer, you can increase your soil organic carbon stocks by 10,000 times, but all you have to do is for 1 hectare buy a 10 million euro robot. This will of course not be implementable. Nobody will do this. This is where the economic carbon sequestration potential will kick in. We want to take into account all the implementation costs, the maintenance costs, but also the benefits from introducing a certain measure. And this will give us a potential area of implementation where we actually can put a measure into place. Here again, the example of cover crops. What data will we use? We have a two-tier approach in CarboSeq. The first one we will calculate on EU available data, and the second one on national data sets, which are usually much better in quality. Today, I will just talk about the EU data. Here, for example, we have some data sets from Eurostat. So how could we get to this area of implementation for the cover crops from a biophysical point of view? Here we can see we have information on bare soil. So for example, if we have bare soil, agricultural soil, of course, then of course we can implement cover crops there. Another approach could be, or an additional approach could be the cover crop information on the top right. We know where are cover crops. And basically you could say where there is a lot of cover crops, there's a potential for even more cover crops because they grow there. We could also try it the other way around and say, okay, where do we have winter crops? Where we have winter crops, there we can't have cover crops over winter. Just to give you an idea on how we are working on this. But the next question after the area of implementation is what actually is carbon sequestration? What is climate mitigation? What values do we want to deliver in the end? And there are basically 4 scenarios. In the top left, you have the graph A. You can see on the x-axis the years and on the y the SOC stocks. So let's assume our business as usual is in a steady state. So that's our baseline. If we implement a measure that increases soil organic carbon, then we can get an increase. And there in blue, you see the climate mitigation effect, and in orange, the C-sequestration effect. And you can see there, it's very simple, very straightforward. In the top right picture, you can see what if the business as usual is not yet in a steady state, but still there has been another measure introduced before our measurement time. So it's still increasing there, the SOC. But after the implementation of the suggested measure, we have an even higher increase. So compared to situation A, you can see we still have climate mitigation and carbon sequestration, but a bit smaller than before. Now let's go to the bottom left. Here it gets really interesting. What if we have not a steady state, but we actually lose carbon? So with our practices that we do at the moment. So we have a loss of carbon, so there is no sequestration happening, as no carbon is uptaken from the atmosphere and actively stored in the soil. However, as you can see, the bottom line there is our business as usual scenario. And if we implement an agricultural measure to increase SOC, we still have a climate mitigation effect. But as I said, no sequestration. And now on the bottom right, we have a mix of both of the three scenarios. We could say, compared to the time point 0, we have carbon loss in the business as usual scenario. However, after implementing an SOC measure, then we have actually uptake of carbon from the atmosphere. So here we have then also a difference in the potential of climate mitigation and carbon sequestration. So lastly, I would like to show you what measures we are looking at in CarboSeq. We're still working on the database analysis. However, this is, let's say, our top picks that may be included. So we will look, of course, to cover crops, high carbon crops and rotations, intercropping, crop residues. The no-till, reduced-till is still under discussion, as the data from long-term experiments is not clear. So we need to analyze a bit more there. We look at irrigation, at agroforestry, biochar, and also land use change. So we basically, in work package 9, we create these emission factors based on long-term experiments data, the LTEs. And we also, with the area of implementation, find a more feasible area on where we can implement a measure. And this data will be put into a Roth-C model so that we create a new soil organic carbon modeling that brings us closer to reality and away from these theoretical potentials. And with this, I would like to finish, and I'm waiting for your questions.
Thank you, Felix, for a very nice overview of the CarboSeq project. I'd ask people to use the question and answer function to input your questions for Felix or for all the speakers as we go along this morning. So I have a question to start off, Felix. In terms of, you mentioned the management options and you know, the need for region-specific management options. How will the CarboSeq project, I suppose, work in terms of both land use, soil type, and the climate differences, and bring that all together?
Very good question. Thank you. Yes, so of course we consider that. This is all included in the Roth-C model. There you have all the soil types, texture, and climate going in, but also the management options. For this, we use European data sets that are available. And yeah, so this will be considered. And in the end, we will deliver. We are not sure yet, as we need to see what kind of data we can get for the management. This is always the tricky part, but possibly on a NUTS level, for example, NUTS 3 regions or so, although we try to go for raster points, that we give really, let's say for each raster point, we want to give suggestions. What can you do? How much does it cost? Is this a feasible measure in that raster point or not? Based on the pedoclimatic region.
Okay. A couple of questions coming in here, Felix. One from Natalie. Could you please elaborate on why you decided not to include organic amendments?
Yes, that is a very good question. Of course, organic amendments would be a choice, but we need to consider we want additional carbon input to the soil. And what are these organic amendments consisting of? Basically, it's plant residues that have been, for example, fed to animals, and their dung will be brought back to the field. So in a sense, it is still the plant residues, just in a different form on the field. So this is not really additional. So we will have these leakage effects. For example, if we would, just crazy scenario, if we would put all over our fields, organic amendments, they need to come from somewhere. They need to have grown somewhere. So we could, of course, import it from, let's say, outside the EU, However, then basically we're just reducing it from wherever we take it from, and then they will have a negative carbon balance. So this is the reason why we will not consider organic amendments, because of these leakage effects.
Okay, something along the same lines, the feasibility of biochar, maybe a comment on that. And, you know, the question from Leonardo here, does it seem suitable only for small areas?
Does what seem suitable?
Biochar, Felix.
Okay, I see. Well, that depends. This is what we want. This is also one of the tricky measures we look at, because putting biochar, it's not or anything really. It's not always just about carbon and climate. It's also about the side effects. And for example, with biochar, one problem is they are contaminated, and you can only put this to a certain amount on a certain area to stay within, let's say, healthy soil levels. So there is a limit, and we're not sure yet which scenario we want to model. For example, we could say we want to put 200 kilos per hectare of biochar on a field. That will certainly increase the SOC content, but it will also pollute the soil. And also, where does that biochar come from? So we're looking at also combining measurements. For example, I mentioned the agroforestry. So from these hedgerows, for example, you create additional biomass. From the cuttings, you could make them to biochar and then put them, doesn't matter where, but you know, you could do that. So these are exactly the questions we're working on.
Okay. One from Peter Kuytman. What is the reason that you only identify actions to mitigate to contribute to mitigation that come at no cost? In your own words, he says, we check that all the costs associated with these actions. And Peter's comment here is, I guess climate change mitigation is not free for all. And do you have a comment to that?
Yes, he's absolutely right. But the thing is, we want to be as realistic as possible. And in the end, who is it who decides what happens on the field? The first step would be the farmer. So we have to convince him, for example, to plant hedgerows. And farmers notoriously dislike hedgerows because they can't use their heavy machinery and they lose field and therefore yield. So that's why we want to, so we create, it's called cost abatement curves. So you get a curve where you can see this is the point of break even, and from here you earn money, and from there you lose money per hectare. And then let's say everything above that line, we could assume, okay, this is likely to be adopted by a farmer. Maybe everything that is plus minus zero, well, the farmer may ask himself, why should I change my whole crop rotation, for example, to increase carbon if I don't see the benefit? Let's say I'm 60 years old, I only work 5 more years, I don't want to do that. And everything that goes into the minus, the farmer will just say, no, I lose money. And this is then where the policy needs to take over, either with incentives or with, basically making it mandatory for all farmers to, let's say, introduce hedges. Okay. So that's why the costs are important.
And we will hear from a farmer's perspective later on in this session, so that'll be quite interesting, Felix. To get on to the modeling side, we have a couple of questions just to briefly explain what model the project is using or are going to base its estimates on. And I suppose, can you give an indication of accuracy and variability of the estimates and the system in terms of region specificity, etc.?
I can tell you all of that in about 3 years at the end of the project. But the model that we use is Roth-C, and we are working also on improving it. So we built our own model toolbox, and we will test it on ground truth data. So for example, soil inventories of some countries like us in Germany, we have a very good one in Denmark or in France as well. So there we will train the models and we test them how accurate they are predicting. And this will happen this year. As I said, at the moment, we are analyzing the database to select the measures that look most promising.
Okay.
Then we will have the test runs this year. The model toolbox, as far as I know, is about halfway done. And it is planned that then in the next year, it is run on all of Europe, plus given to all of our partners, and they can use it on their own soil inventory data, because there's also data protection laws, so they're allowed to use it, but we as a different or a third person, we're not allowed to use that data, but we're allowed to use what they have calculated.
Okay, okay. One has come in here from Christine Muller. What key EU cropping regions, what are the high, for these regions, what are the high carbon crops in the rotations? I don't know whether you have that information at this point, but you might make a mention. And then another question, how long would each practice be effective in terms of reaching, I suppose, carbon accumulation?
Okay. The first question, let's start with the second one.
Okay.
For how long? That is a good question, because when is this steady state reached? This is a theoretical thing. So we will run the model and fiddle around, but let's say we will, in the graph, I wrote 25 years and 50 years, just that we have, let's say, a near future scenario where people that live now, the farmers that are working now, may be interested in. Of course, when do we reach this steady state? This can be in 100 years, this can be in 200 years. This is what the model in the end will tell us when we are at this plateau level. But yeah, it is definitely a long-term process. This is nothing we can do from today to tomorrow or within a year. And I need the first question.
The first question is for certain regions, we'll say what high carbon crops might be available, or which crops might be more preferable, I suppose, is to paraphrase the question.
Yes, there we're working on it. What we will suggest, because the first problem here is we need to get management data. We need to know what are the typical crop rotations for each, let's say, nuts 2 region, so that we can see what is there right now, and then we can suggest how to increase it. We're also still discussing if we maybe not go for high carbon crops, but if we maybe go via, let's say, the protein strategy, that we say we want to increase the legumes in the crop rotation, so that we can give a more, not just a random number, or we want 10% more high carbon crops in the rotation, but that we can say, okay, the EU goal to reduce, for example, soy inputs, or to increase protein by plants is the following number. And then this is a scenario we can model based on real aims of the EU.
Yeah, and offsetting of chemical fertilizer, etc., with legumes.
Exactly.
And that. Final question then, before we finish this session. Has soil biology been considered? Soil bacterial versus fungal biomass have different impact on carbon and plant biomass. Just a comment, please.
This is beyond the scope of our modeling. However, there are other projects within the EJP SOIL program that do take care exactly of these issues. But this is out of the scope of CarboSeq.
Okay, thank you very much, Felix, for a very informative starting presentation for the workshop. Thank you also to the audience for the many questions that have come in, and any questions